Yes, yes.
Great. So let's start this session. Today's session is on feature selection and feature engineering. Uh, The learning objectives for today's session are you should be able to list advantages and disadvantages of feature selection. You should be able to list basic types of feature selection. You should be able to write the formulae for few feature selection tests such as t-test, AIC. A lot of it you have already covered. And then you should be able to write the steps for feature selection procedures such as forward selection, backward elimination, and objective function for lasso, elastic net, etc. And you should be able to write the steps for PCA, principal component analysis. Okay. In addition, you should be able to know about basic uh, feature extraction methodologies for three common types of data, which is images, speech, and text. Okay. All right. So let's get into it. So why select features? Okay. So here are some advantages of feature selection. Many times you get data where you have too many features. So let's say you have 100 features for a data set, and especially if the number of samples is low, a lot of features can cause overfitting. And even if you don't have a whole lot of even if you have a good number of samples, a lot of features can still cause confusion. They can cause problems due to collinearity. Collinearity means two features are correlated, highly correlated, so you don't know how to interpret their coefficients. And it can increase the training time if you have too many features. And interpreting your models can be a pain if you have too many features. So the advantages would be reduce overfitting, reduce confusion, reduce collinearity, reduce training time, and simplify interpretation of models. But then there can be disadvantages of feature selection. And what that means is that you can inadvertently throw useful information, because any feature selection method comes with its own biases and assumptions. Okay. All right. How do I annotate the screen? Manage stock caption. Hmm, doesn't show screen annotation. Okay. So here is a pictorial representation of a classification problem, binary classification problem, that tells you how features can be problematic sometimes. Okay. So for example, let's say you have two variables. This is x1 variable and the vertical is x2 variable, right? So you can see that here in the first case, there is no variance in the x2 variable. It has roughly constant value for all sample points. So in such a case, your x2 variable is useless. One of the dimensions can be useless. Okay. And if you're doing just classification, so if you look at this second example, although there is variance in x2, okay, there's variance in the vertical feature dimension. There the points, the red points and the blue points, the red rhombuses and the blue circles, they're quite interspersed in the x2 dimension. Whereas in x1 dimension, you see some order that mostly the blues are towards the right and the reds are towards the left. So this would be another case, even if you have some variance in a feature, and let's say you normalize the features, even then you can, one feature can be completely useless. So here vertical dimension seems less useful than the horizontal dimension. uh, and another scenario can be that you actually have x1 dimension and x2 dimension, but the data is actually distributed in another direction, which is a combination of x1 dimension and the x2 dimension. So in that case, rotating the axis may be useful. So you may not want to go with the two original features, you may want to actually find a new feature that's a combination of the X1 and the X2 feature. Similarly, in the last case, you can see that the hyperplane is actually along this direction, which means that if I project everything along a line that goes like this, then in just one dimension, I can separate the two sets of points. So all these point to the idea that we need to play with the features, we need to eliminate features, we need to maybe recursively add features, we need to find combinations of features and so forth. Okay, so original features may not be useful just as they are. Any questions? And this is true for both classification and regression. Right? Yes, Joydeep. Joydeep?
Sorry, I was on mute. So I was talking about, is this the, for example, if we have a set of data and
Yeah.
we have to select what will be the number of features that we are going to select. So is this the feature selection for that, or I mean, in general, we are talking about that?
No, it is for that. It is precisely for that.
Okay.
Yeah.
So it means when we are previously when we are selecting features which are more important, for example, in the Titanic dataset, like whether the cabin or the passenger or the ID will be important or not, we are checking collinearity and other related stuff.
Yeah.
Is it similar thing we are going to do in a more methodical way?
Yes.
Okay. Okay.
Yes.
Thank you.
Okay. Prasun?
Hello, sir. Can you explain how in the second figure one of the dimension is useless?
So look at the vertical dimension, right? This x2 dimension. So one of the inherent assumptions of machine learning is that there is some contiguity in in uh, in space, right? So things that are closer to each other in some sense are either in the same class or have similar regression values. So here you have green. So if you project it along the vertical dimension, you have red, then you have blue, then you have blue, then you have red, blue, right? So it's quite interspersed in the x2 dimension. It's not like if I can draw a line in the, which is like a horizontal line, I can get more pure on the upper part of of that line and the lower part of that line. Whereas if I draw a vertical line, I can get more pure reds here and more pure blues here. So in that sense, the vertical dimension, the x2 dimension is not that useful. X1 dimension is more useful.
Okay, sir.
Okay. So in general, in machine learning, if I plot number of features selected on the x-axis and I plot some measure of usefulness or goodness of fit, okay, in the y-axis where higher is better, uh, then what I find is that when you have too few features, your models don't do very well. But then there's an optimal number of features where it does very well, and then there is actually some confusion that sets in if you start to have more and more features. So there is usually an optimal number of features, and that's what we want to explore more today. Okay. uh, but the problem is little more complicated than that. It's not just the number of features, it's also the subset of features. So if you can extract 1,000 features from an image, it's not just that 20 features are useful, it's also that which 20, right? And which subset of 20. So you have 1,000 choose 20 different subsets, and out of those, one of them is the optimal one. Okay, so there's a comment by Abhilash: for the analytical methods inverse XX to exist, should features be linearly independent or should samples be linearly independent? So you're talking about the pseudo inverse. For the pseudo inverse, the features should be linearly independent. Okay. So there are different ways of feature selection. Okay, one of them is called filtering method. The way to think about filtering method is that here you are looking at each feature in isolation of other features. You're not looking at features taken together. Okay, so the basic idea is to remove useless features or include useful features, and remove redundant features or include non-redundant features. Okay, so the question is, what makes a feature useful and what makes it non-redundant? Does everyone understand the word redundant? Redundant means something that does not add new value. So when we say that in a company, these people have been made were redundant and we are reducing redundancy, that means their work was already being done by other people and we were paying them regardless for doing no value add. So that's a euphemism that is used when downsizing in a company happens. So similarly in features, let's say if you have one feature that is a combination of two other features. So let's say x3 is x1 plus x2. So in some ways, the information in x3 is already contained in x1 and x2. So x3 is a redundant feature. So what makes it non-redundant? Okay, and what makes a feature useful? All right. So that's what we want to define slightly more formally. So the general outline of the algorithm would be that you would loop through all features xi. So I is the dimension or the ith feature, not the ith sample. Okay, ith feature. So we'll loop through all features xi and compute some measure of utility and non-redundancy, and let's call it mx sub I, and sort all features based on this measure m, and pick the top k features and don't include the other features. Okay. So that is basically the whole filtering idea. Okay. All right. So now let's look at what are some measures of usefulness of a feature and non-redundancy of a feature. Non-redundancy is a little difficult to define, but let's talk about usefulness. So if you are trying to solve a regression problem and your target variable is y, then the first thing that comes to mind is your feature xi. Here, pardon, I haven't included I, but let's say xi. Is it correlated with the variable y? So what that means is that I will compute this covariance of xy, okay, and divided by the square root of variance of x and variance of y. Okay. Um, so that is a Pearson correlation. That means if I plot x and y, x at the x dimension and y at the y dimension, I will I will get a straight line if this covariance is high. Okay, if they are very correlated. Now it's possible that I actually don't get a I don't have a high correlation, yet there is a very strong relationship between the two. So let me give you an example. Give me a second. Let me start uh, PowerPoint. Sorry, because then I can annotate. Okay, so let's take an example where you have this x-axis and then you have y-axis. Okay, your points are distributed in such a way that they are not sitting on a line. Okay, but there is some sort of a one-to-one relationship between x and y. Okay, so here, and then let's say there are some outliers also, but they still keep following some trend. So what that means is that if I take ranks of x, right, I'll look at the order of x. Sorry, not this one, not this one, but this one, this one, this one. And I look at the ranks of y, right? Then the ranks are very correlated. The xy Points themselves may deviate from a line. Okay, so the XY points themselves may not lie on a line, but it lies on a curve enough that if I stretch that curve into a line, then they will be very correlated. Okay, so that brings us to this
This is
idea. Go ahead.
this is not clear. Can you explain a bit more?
Yeah. So basically, I'm trying to come to this another correlation metric, which is called Spearman correlation. So what that says is that I, instead of finding covariance of X and Y, I will find the covariance of rank of X within all the samples and rank of Y within all the samples. Okay. And the ranks are very correlated. So the rank now is not very, it's a robust to the shape of the curve. Okay. So coming back to this example, uh, give me a second. Okay. So if you have x-axis and you have y-axis, but your points lie something like this, right? So you can see that they don't lie on a line, but if I take their ranks, right? What is rank? Rank is the order on which they fall on the x-axis. Okay. And if I take their ranks, which means the order in which they fall on the y-axis, right? So now what is happening is that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, although this distance is very high. Okay. Similarly, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, although this distance is large and this distance is small. Okay. So now if I take their ranks and I take the correlation of their ranks, then that's going to be a higher correlation than if I were to just take the raw X and Y values. Is that clear? Okay. So that's the difference between Pearson correlation and Spearman correlation. So Spearman is more robust to outliers and more robust to scaling of one dimension and so forth. Okay. So these are two measures you can see to find which feature xi is better related to yi and is a better use of including that as opposed to another xj. Okay. Any questions? All right. And if you're doing classification, you have already looked at hypothesis testing, right? So you want to see for which features are the means sufficiently far apart compared to their variances. So which is the t-test, or the ranking of the of two different classes is different. So what you see on the left is one Gaussian curve for one class and the other Gaussian curve for another class for one feature. So let's say that feature is xi. So what you have on x-axis is xi. What you have on y-axis is the distribution, frequency or probability of xi. And red curve is xi given class C1 and blue curve is xi given class C2. So what you can see is that the peaks, if you look at the peaks, which is the mean of the Gaussian, is so much far apart. But then you also have to look at the variance of the red curve and the blue curve. And that is what t-test computes, which we covered in the data science module. Okay. So a useful feature is the one that gives you higher t-test value, magnitude of t-test value. Just like in the previous example for regression, a useful feature was one that gave you higher Pearson correlation or Spearman correlation, as the case may be. Okay, so there is some subjectivity involved in which test to use. Similarly, you could look at Wilcoxon rank test, which was also covered, I believe, in the data science module. And based on that, you can see which features are more likely to be different for two different classes. And based on that, you select that feature and eliminate those where the difference in the feature value is not that much between two classes. Any questions? Okay. So I'll go back to this algorithm. You'll loop through all the features. You'll compute some measure of utility, which is either the correlation or correlation for regression, or t-test, let's say, or Wilcoxon rank test for classification. And you will sort the features based on that measure and pick the top k features, and then you will decide to include them in your model. Okay, so this is a
On
filtering based method. Yes.
how to test
Question?
non-redundancy.
Yeah. So I haven't.
Non-redundant.
Yeah, I haven't talked about that. I'm coming to that. Okay. So redundancy. For that, you look at data correlation. You look at so what is x-axis and what is y-axis in this figure. X-axis is all the features, xi basically x1 to xd for d dimensions, and y-axis is also all the features xi to xd. And each each ijth quantity on this matrix, which is defined by this color, let's say -1 to +1, is the correlation between or cross correlation between xi and xjth feature. Okay. So based on that, there are tools that will give you this block diagonal structure where they will show you more correlated features together. And so blocks, so this is a block. In this block, most of them are green. That means most of them have high correlation. And then you have another block that in which most of them are green, which have high correlation. So look at this particular sub block where there is a lot of green, which means lot of high correlation values. Here, not all three features here are useful. Or look at this one, for example, this block of 2. This is highly correlated. This block of 2 is highly correlated. So when you see such blocks, these are redundant features. You can use only one of them and you'll be fine. Okay, so you do some sort of a clustering, and clustering is not something that we have talked about till now. We will cover it later in ML. So basically you will cluster features where the features in a single cluster are highly correlated with each other, and they are not so correlated with features that are not in the same cluster. And then you can select only one variable depending on which one is more interpretable from the cluster to represent all the other features, and not use all the other features. So remember, if you have a model with x1, x2, and x3, and x2 and x3 are perfectly correlated, then the weight of x2, w2, and weight of x3, which is w3, there is some ambiguity in that. You can add something to w2 and subtract the same thing from w3, and you will still get the same prediction value, y or y, right? So these x2 and x3 will be redundant, so one of them can be eliminated. Okay, any questions?
I may have missed. So what what we are talking about, the rank of a feature, for example, if it is age or something. So what practically we understand by a rank?
So rank would be, so let's say if you are doing a regression problem, rank would be the feature that has the highest absolute value of correlation coefficient with the target variable. Or if you're doing classification, then it is the rank would be the feature that has the highest t-test score, absolute value of t-test
Okay,
score, right?
okay. From
With,
in that sense. Okay,
yeah,
okay.
with, yeah.
Mhm.
Okay. Ashish?
Sir, so in this case, Spearman correlation is always better than Pearson.
Spearman, yes, many times it gives you better results, right? If you have strong reasons to believe that your regression model should be linear, then you would use Pearson correlation.
But in general sense, Spearman is better.
Yes.
Thank you, sir.
Okay. Let's look at some chat. Mm, what is rank? So I think that is covered. How does the distance of a point from featured access relate to rank? Mm, oh, rank. Okay. So rank was for data points. That was not for features. So rank is just the order. Which comes to the left is rank one. Whichever comes to the right is the highest rank, or the other way around. So that's arbitrary. The direction is arbitrary, but it's based on the order in which they project uh, onto the axis. How do we find rank when there are multiple x and one y? So if you have multiple x and one y, you discard all the other x, you take only one x, and you look at its rank, and then you look at the rank of y. So what I mean by its rank means its rank for different sample values. So remember, you have a data table. Let's switch to the other thing. Right. So basically, you have a data table, right? So you have what's that pen? You have a data table. Okay, so this first column is y. No, I can't write it here. I'll have to clean this up. So I have y, right? So I have sample one, sample two, all the way up to sample n, and then I have x1 all the way up to xd, right? So I have some value here, some value here, some value here, and I have some value here, right? Um, and then I have some value here, some value here, some value here. So I pick this particular feature, and I pick this the variable to be predicted, and basically I assign them ranks. Okay, so the one that has the highest value will be rank 1, the one that has the lowest value will be rank n. Okay. And here also I do the same thing. The one that has the highest value will be rank 1, the one that has the lowest value will be rank n. Okay. So that is what I mean by rank. So now I can take the correlation of these ranks and these ranks. Is that clear? Abhilash?
Sir, highest value in terms of magnitude or the number of values?
No, no, actual value, not magnitude in this case.
So the feature having the largest value will
Yeah.
have a higher rank.
Yeah.
Okay. Thank
Yeah.
you.
Depends on whether you want to do it in the ascending and or descending order. That doesn't really matter. But just be consistent. All right. Okay, so the next set of methods are wrapper methods. In filter methods, we looked at each feature in isolation. We looked at x1, x2, x blah blah blah, xi, blah blah blah, xd. Right? So from 1 to d, we looked at them in isolation. Now what we'll do in wrapper methods is we will maintain a model, and we will look at each feature in the context of a model. So it will be inside a model. Okay, so it will not be like a simple correlation between xi and y. It will be basically a subset of features and whether how good they are in predicting y. So we'll add or remove features, and we will measure model accuracy. And the model selection criteria will be k-fold cross-validation, AIC or BIC. So what are these? Okay. So what this means is that, let me again go back here. Okay. So what I mean here is that I have these features x1, x2, all the way up to xd, right? And then I have sample 1 all the way up to sample n, right? And I want to predict this variable y or t. Let's just call it y. Okay, I want to predict y. So y1 to yn, right? So this is what I want to predict. Now, what I want to do is I want to take some subset of these. So let's say I select two variables and I will call them subset S. Okay. So I want to see what is this subset S that will give me the best way to predict Y. Okay. So this subset S is what I'm interested in. And so how many subsets can I have? I can have 2 to the power D subsets, right? So any feature is either in the subset or it is not in the subset. So I have 2 to the power D total possible subsets. And out of these total possible subset, 2 to the power D subsets, I want to find out which one is the best. So for all 2 to the power D subsets, I can fit the best possible model. So I have these models MJ, okay, where J belongs to 1 to 2 to the power D. Okay. And for all these models, these are the optimized models for that subset. I want to pick the one that is the best model. Now, what is the criteria for that best model? That's what we are looking at. Okay. So first of all, this is cost prohibitive because it's exponential in D. But let's say somehow if I could do that, then how will I pick the best model? So there are three criterias. One is k-fold cross-validation, the other is AIC, and the third is BIC. There might be more criteria, but these are the most commonly used ones. So what is k-fold cross-validation? So you're already familiar with this one. So basically what you do is, let's say we are doing 5-fold cross-validation. You would divide the data into 5 folds. What is data? Data is the n different points. So the first n by 5 will go in fold 1. The second n by 5 will go in fold 2. The third n by 5 will go in fold 3 and so forth. And you go through all these 5 folds where one fold is held out for validation. The other 4 folds are used for training. If you had 3 folds, then you would have 2 for training, 1 for validation. Okay, let's see what's in the chat. For that to make any meaning, that category might be ordinal. If the data is categorical, what's the question? How do we find the rank? Okay, that I have covered. If the curve is not monotonically increasing, will then also Spearman correlation give us the correct answer? Probably not. Then Spearman will not give you the correct answer. If the data is categorical, then you will not use Spearman correlation. You will use t-test or something else. I don't think we can find correlation of categorical variables. Yes, because you will use t-test or something else. I think we have to encode them into integer and find the correlation. No, you don't encode categorical variables into integer and find correlation. You use another test like a t-test or a Wilcoxon rank test. Okay, let's come back to this. So in k-fold cross-validation, you would divide the data into k-folds, and then for each model, you will run 5 different training runs. One on fold 2 to fold 5, the second on fold 1, fold 3, fold 4, and fold 5, the third one on fold 1, fold 2, fold 4, fold 5, etc. And you will find the result, the validation result on fold 1, fold 2, fold 3, fold 4, and fold 5. Okay, so this is for 5-fold. You could also do 3-fold if you don't have that much patience. Okay, and then you would look at the overall result of these 5, the one that gives you lowest average error or highest average accuracy, and also a small variance in accuracy, let's say. Based on that, you will say that this model is good. And if you have to look at all possible subsets, you have to do this for 2 to the power d different models. And if you have hyperparameters in that, then 2 to the power d times the number of hyperparameter settings that you have. Okay, so it's quite cost prohibitive, but that would be the best way to find the best subset. Okay, so this cross validation only looks at the accuracy or whatever is the measure. It doesn't look at the complexity of the model. You could get high value for you could get high accuracy value, but for that you might need to use a lot of variables. So this is remedied. The idea of simplicity of the model is remedied by two different measures. One is AIC, uh, AIC information criteria. AIC was the name of a statistician who proposed this, and the other is Bayesian information criteria. Both are quite similar. There's just a slight change in the formula. So basically, what they look at is the likelihood. Okay, so the model that gives you good likelihood is the one that has good information. All right, and also that it should use less number of parameters or less number of variables. So 2k, where this is your number of parameters, and minus log of L. The only change that happens between AIC and BIC is that instead of k, it is k times log of n, where n is the number of samples. Okay, so both penalize if you have high k. If you use more complex models with more number of variables, it penalizes that. But it also but both of them want high likelihood for the data. So what is likelihood for the data? In t-test it would be how that formula for fitting a Gaussian on the data. Okay, so these are different ways of looking at which subset is good. Okay, so you are also looking at the size of the subset, which is k. Whereas in k-fold cross validation, that k was not the size of the subset, that was k was the number of folds. So you're not looking at size of the subset in k-fold cross validation. Right. Okay. Then if you don't want to look at all 2 to the power d subsets, then there are some greedy methods to recursively uh, add features or eliminate features. One of them is forward selection, where you add features. The other one is backward elimination, which is just an analog of this, where you eliminate features. So what you do is you start with a naive model where you have a set S in which you have no variables at all. Okay, it's completely empty. And then all the variables are in this parking lot, which is set A. Okay. So now recursively you add the best variable to set S, and you keep adding until your model does not improve. All right. So let's go back to this curve. So ideally you would start somewhere here. Your model will be very poor. You will add some variables, your model will improve. You'll add more variables, your model will improve further. You'll add more variables, your model will improve. And then it will kind of saturate. And it's possible that it will either improve very slightly or it will start to even deteriorate. Okay. So if it starts to improve only very slightly, then we don't want to make it too complicated. We want to just stop there. Or if it starts to deteriorate, then definitely we want to stop there. Okay, so this is forward selection. Any questions? Let's look at chat. Prasoon, what's your question?
Sir, so first we select the number of subsets and then we train the model, and then we calculate the accuracy and then go back again and select the number of features again. Is that the process of selecting?
No. So actually it's the process is quite painful. You have to fit the model every time. So let me show you what that is. Let me look at if there is any chat. The less the AIC VIC, the better. Yes, and the K-fold validation we are looking at all combination. No, all combinations of features in all folds. Yes. Let's look at if there are any questions in YouTube. No, there is no questions in YouTube. Let's come back. So I will now tell you the procedure in more detail so that it's clear. So basically what we are doing in forward selection. So let's say if set S is empty, that means what is your model? Model is nothing but just a bias. Okay, you cannot include anything from the variables. You cannot assign them any weights, nothing, right? You can only include, you can only have a bias. So this is your empty like model which just has an intercept. It's just a constant. Okay. Uh, so now what you do is you loop over all the variables from 1 to d, and within that you look at all the variables in the set A. Okay, so A is now holding all the variables in the beginning. Compute a measure M for adding the variable, let's say the first variable from set A into S, then the second variable from set A into S without, so when you add only one at a time. It's so let's say if it was variable x1, then you test for variable x2. At that time, you don't include x1 again in S. You only do for x2. Okay, so let me show you in a better way. So let's say we are here, right? So you have empty set S, okay, and then you have set A that has all the variables x1, x2, all the way up to xd. Okay. So in your first iteration, you are first testing whether if I include this, then what is my measure M1? If I include this, what is my measure M2, etc. until I find what is the measure MD. The one that gives you the best measure, so let's say M2 gives you the best measure, you include that in S, and in your next iteration, this will have X2 and A will have X1, not X2 but X3, and then all the way up to XD. Okay, now you are testing on all of these. Again, you are testing your measure M. So what you are testing is, what if my model has X2 and X1, or X2 and X3, or X2 and XD. X2 is now included already. Okay, so in each iteration, one variable has already been included. You test for inclusion of one variable from all the other variables that were not included. Okay, so how many total tests you have to do? You have to do, in the first case you have to do n tests, in the next case you have to do n minus 1 test, in the next case you have to do n minus 2 tests, all the way, sorry, not n, d minus 1, d minus 2. Okay, so it is d times d minus 1 by 2, right? So d choose, like, so basically all these tests you have to do. Let's go back to some questions. Who has raised hands? Please ask your question. Neeraj?
Sir, I don't have the question from this point. I have the question where you were explaining the, like for linear regression, you were explaining the points if it comes in a curve shape.
Yeah.
So in that case, how will we proceed? This is the way we proceed. Like I'm still confused. Is it like I mean, for linear regression, I've read that until and unless the shape is not, data shape is not coming in linearly, then we can't go ahead with linear regression.
Yes, but how would you know that it is coming linearly, right? Because nothing is perfectly linear. There will be some noise around the linear, right?
Yeah.
So I'm not talking about the form of the model anyways. I'm not saying that should you use linear regression or should you use non-linear regression. In linear regression, out of the d variables, which subset should I include? That is what I'm trying to answer.
So by this, we have to check every time that the shape is coming linearly or not, is it?
Yeah, of course, of course. So every time you are basically fitting only a linear model. If it was a non-linear model, then every time you would be fitting a non-linear model, such as a random forest regression or a support vector regression.
So somewhat I have read that even if the shape is not linear, you can go for transformations and all. What is that?
So that is different. So that is
Okay.
yeah. So that is basically, you can, if you have x1, you can also include x1 square, x2, x1 cube, and then you can fit on x1 square and x1 cubed as if they were x1, x2, x3, and what you will get is a polynomial regression as opposed to linear regression.
Okay.
So that is what is meant by including feature transformations. Okay. So question from Yeah, let's Ashish, or Abhinandan, what's your question?
Sir, basically, I have a question in selecting this subset of features have given the optimal result. Like, firstly, what we did, we had a D number of features and we uniquely go individually one by one, X1 to X3, and we found X2 giving a higher M value. Like, say it's a
Yeah.
measure is good. Now you
Yeah.
have selected X2 and separated. Again, you are looking at X1 to XD except XD. But my question is, can it be like, okay, individually X2 is giving a better measure, but if we select two features, X3 and X4 is giving better result, but how
Yes.
will we getting X3 and X4 because we have already taken X2, right?
Yes. So that is a flaw in this method. That's why it's called a greedy method. It's
Okay.
greedy. It greedily includes one variable at a time.
Okay.
Okay. So that's a flaw in this method. Okay. Ashish?
Sir, in the case of AIC and BIC, the likelihood is synonymous to some performance metric, right? Like for example, accuracy or something in
Yes.
application sense.
So in application sense, they actually use a parametric form like fitting a Gaussian class conditional so that you can compute uh, the likelihood in exact terms.
So that is in probability. Like if we are modeling probabilistically, then it would make sense. But for example, I just want to implement this idea just like
Right.
a good metric so that
Right.
my number of dimensions is also taken care of. Then I can kind of replace the likelihood with accuracy or something like that, right?
Uh, Whether you can
Would it
replace
make
it with
sense that way?
accuracy, I don't think so. I think you still use you try to fit some parametric form.
Okay, so this is applicable in pure probabilistic
Yeah,
sense.
yeah, yeah.
Thank you.
Gaurang?
And this number of dimensions
No,
is actually coming from Occam's razor, right? The 2K part, the first thing.
no. So if you have d dimensions, then how many subsets you have? You have 2 to the power d subsets.
Now I'm talking
It's,
about AIC and BIC.
yeah, yeah, yeah.
Okay.
So yeah, the initial k or k times log n is coming from Occam's razor. Yeah,
Yeah,
you want to include less of them. Yes.
thank you.
Okay.
That,
Gaurang? Yeah.
so that ranking, you were keeping a few feature from all the features that can be done by PCA, right? Principal component analysis.
So let me come to principal component analysis. It's not a feature selection, it's a feature combination method, right?
Okay.
So yeah, we'll come to that.
But
I'll
a
cover it.
few those who are hmm,
Hello?
those who are which are actually affecting you are keeping a few features which are actually affecting the probability, like the
Yes.
classification
Yes.
purpose,
Yes.
that can be chosen by PCA also, no?
No, it's not that way. So the clustering and keeping some variables and eliminating some variables is different from PCA. PCA does not eliminate original variables, it eliminates some transformed variables. Okay, so
Okay,
let me come to that. I think it will be clear when we come to that.
okay.
Okay. Prasun?
So, what if a certain variable means the target variable depends on the square or cube of a certain feature? Then means how means we need to select that feature twice, or like
No, no.
once only we can do it.
Depends on what your model is like, right? So if your model is linear, then you are in trouble. Then you are not going to be able to model it unless you add a dummy feature which is actually square of xi. It's
Okay.
xj, but it is square of xi. So usually we don't do that because if we had that insight, that means we already know something about the model. Usually we don't have that insight.
Okay.
Kasina?
Sir, could you please go over AIC and BIC once again?
Yeah. Let's look at the, okay. So AIC and BIC are basically information criteria. And basically what they say is that a feature that gives you good likelihood is a good, so these are like negative features in some sense. So your likelihood, if it is high, then it is a good feature. Okay. But
Sir,
not
sir,
only,
one minute.
yeah.
Yeah, so for a feature, we are talking about likelihood, right? So,
No, I'm sorry.
uh,
Let me put it back. Let me go back. A model is good if it gives you high likelihood for the data that was given, not a feature, a model. So the
Okay,
model
so
is
what?
based on subsets. The model is based on subsets of features. So
Okay,
let's
so
say, yeah.
what do you mean by likelihood for a model?
So
You said
likelihood for a model is basically what we had, for example, earlier, which is so let's say if I have a model, let me go back to that here so that I can draw. So let's say I have a model where I have two classes, and those two classes are based on some assumption that they come from a Gaussian. Okay, so one class comes from here, and the other class comes from another Gaussian, which is slightly shifted. Okay, and it is like this. Okay, so now if I have a point, that point falls here, then its likelihood is this much. If I have a point that falls somewhere else and it's from a different class, okay, so let's say it is now from another class and it is here, then its likelihood is this much. Okay, so if I take these likelihoods and multiply all of them together, assuming that they are IID, or if I take the sum of
okay,
their logs, then that is the likelihood L.
okay, that one which we discussed
Right,
back then, right?
right. So that is the log of L.
Sir, and I had one more question.
Yeah,
This what do we say? Uh, could bootstrapping be any method to deal with hyperparameters? Like bootstrapping, we used it in tree-based models. I know that, but
right,
there we are randomly distributing data, right? So
right.
can it be used as any measure for the hyperparameters?
Yeah,
Sorry,
so
my bad.
yeah,
For the
for
features.
model, yeah. So your hyperparameter tuning, your model subset selection, feature subset selection, they are quite related in the sense that you want to see which one is the best, right? So it is that bootstrapping can also be used here, that you can see that after bootstrapping, if you fit, n different models using bootstrapping for one particular criteria, which is, let's say, a subset of features, then how good is the performance on the left out data sets, left out samples, and what is the variance in performance? So that could be a criteria of some sort. So you can use it.
Okay, sir.
It is almost like cross validation then.
Yes. Okay. Thank you.
Okay. So is forward selection clear to everyone? Let's look at chat. Sorry, I'm not able to go back to chat. Yeah, here. Uh, is in AIC, BIC the likelihood of which event you're talking about? So it's a likelihood of the data. So what is the probability of the data being generated given the model? I did not understand the measure. Does it mean accuracy or something? Yes. So the measure means accuracy or likelihood or something along those lines, right? So it could mean AIC or it could mean accuracy if you're doing k-fold validation. Yes. Um, so again, a question of what is likelihood. So I've covered that. Let's look at there's a question on YouTube. The question is forward selection giving us the optimal model on validation data, or is it a heuristic? It is a heuristic. It is not giving you the best model. It's a greedy heuristic, because just like someone mentioned that you can have combination of two variables that actually work much better than individual variables, and we will not be able to discover that using forward selection. An example is the following, right? So let's say you have two sets of points. You have a set of points, so this is in x1 dimension, and then you have another set of points which is this is in x1 and x2 dimension. The other set of points are all around it. Okay, so in that case, neither in this direction nor in this direction you have a good feature that can separate the two, but together they give you very good classification. Forget about all the other features, right? So it's very difficult to select a pair of variables that work together, and then you can actually have a triplet of variables that work together. So that all that is thrown out of the window in forward selection because it's a greedy approach. It will not be able to discover such um, variables that work together. Joydeep?
So on the forward selection, is this the only way to work with the forward selection? As we know, there are some flaws in that, or we have some other technique also.
I mean, you can try to do this on pairs of variables and see if that works better, but then it combinatorially that the size of the problem keeps increasing.
Okay, and if I understood correctly, for forward selection, the greedy approach is one of the this is one of the best approach that we can take.
This is
Even
a popular approach. I don't know if it is the best approach.
right, but okay,
Right.
okay.
So in some sense, some of these flaws are kind of countered by backward elimination, which is the reverse of this, also called recursive feature elimination.
Okay.
So here what you do is you start with all variables in set S and you eliminate one variable at a time and see the one that least affects the model. Okay. Or even improves the model. So you eliminate that variable from S and put it in A. It's the reverse of forward selection. It is backward elimination. And you keep doing that until your model does not improve or it doesn't degrade or it degrades too much. Okay. So when you compare, both of these are greedy methods. In forward selection, if two variables individually are uninformative, but together they are informative, then you won't be able to select them using forward selection. But in backward elimination, you will be able to keep them together, but it is you start with a very complicated model and it becomes very it's computationally inefficient because you are first fitting in high dimensions and then you are going towards lower dimensions. So you're going on that curve, the curve that I showed in the one of the earlier slides. You're going from right to left as opposed to left to right. See? Joydeep?
So as we are taking all the variables, isn't it a computing intensive approach?
Yes,
Because
yes. So
right.
that's a disadvantage of backward elimination.
Okay.
Yeah. Okay. So then there are other methods. Any other questions on forward selection, backward elimination before we move to regularization based feature selection?
One small thing, can you please tell us why it is greedy for the both case?
Greedy means you are not looking at pairs of variables, you're not looking at triplets of variables, you're looking at one variable at a time and you're looking at only very strictly with one measure M.
Okay.
So it is greedy in that sense. So if you remember your algorithm scores, the greedy algorithms were one that take the best next step, even if uh, foregoing the best step and taking the second best step will lead to an optimal solution later on. Okay, so that is a greedy algorithm.
Okay.
So now let's look at optimization based feature selection or regularization based feature selection. So everyone is familiar with lasso, right? Which is L1 penalty over weights, right? So let's say we are looking at linear regression and you have these contours for linear regression. And so let me go back to the slides here, right? So if we had linear regression and we use lasso for variable elimination, so let's say we had, this was the axis, this was the optimal set of weights if there was no regularization. And let's say that these were the contours of error, equal error. Okay. Now, so you have, and so these are your MSE contours, right? Mean square error contours. And then you also have contours for the L1 penalty, right? So let's say your contours of L1 penalty, those will look like rhombuses, right? So let me find the right ink color. So those will look like rhombuses here, right? These are actually squares that are tilted at 45 degrees. Right? So what we were saying was that wherever, uh, depending on the value of lambda, which is the optimization penalty uh, for the L1 loss, wherever we find that the contour is the contour is at 45 degrees to is tangential to one of the corners here, right? At that point, the other feature will be eliminated. Only this feature will survive because this has a non-zero weight. The other one will have a zero weight. Okay, so that is how feature elimination was going on, and that is basically what is shown here. What is shown here is that you have what is on the x-axis is uh, 1 over lambda. Okay, log of 1 over lambda or minus log lambda, and what is on the y-axis is the value of weight w. Okay, so as you have no penalty on the right hand side, no regularization, all all coefficients are non-zero, all coefficients are in the model. As you keep increasing the penalty and go towards the left, look at the solid curves, don't look at the dotted curves. These features start to get eliminated. Okay, so some of them get eliminated. So for example, this one gets eliminated first, then this one gets eliminated next. So some coefficients are positive, some are negative. Those that become zero are the ones that got eliminated, right? And for very large penalty, all of them get eliminated, which is here. Okay, so this L1 norm is in a family of norms called LP norms. What is LP? LP is basically sum of W to the power P, mod of W to the power P for all variables. Okay, and then you sum them up and you take 1 by P power. So what is L0 norm? So L0 norm is limit of this P tending to 0, which means that L0 norm basically looks at only those values that are non-zero. Okay, it doesn't look at values that are those weights that are zero. It only counts the number of non-zero weights. And L infinity, if you raise this to the power infinity or P tending to infinity, only the highest value of W, the max of mod of W will survive. That will dominate this term. So it will be the max of all the weights. So that is L0 norm and L infinity norm. L0 is count of all non-zero weights, and L infinity is the maximum weight or maximum weight magnitude. And in between you have L1 and L2. L1 and L2 we already looked at. So what L2 does, L2 does not eliminate any variables. Okay, so in this figure, if I have another figure where the L2 norms were circular, and then I had these the L2 norm penalty were circles, and then I had the MSC contours like this, you can see that at every tangent there's nothing that is zero, right? At every time these two are tangential, there is nothing that is zero. So your trajectory of weights would be like this. So no weight will be eliminated, but if I increase lambda, the weights will shrink because they will go towards the origin. Here they will not only shrink, but some of them will get eliminated as I increase lambda. Okay, so that's what I see in this behavior, that some of them shrink, but then some of them also become zero after that. So that is the solid lines for L1 norm. So in some sense, L1 is not only doing regularization, it is also selecting features, because it has the non-selected features, their weights have become zero. Okay, but what happens if you have features that are correlated? Which one will get eliminated of the two correlated features? So that's a problem with L1 norm, in the sense that if you think of two weights, right? So if you have two variables that are perfectly correlated, so if you have x1 and x2 that are perfectly correlated, right? So if I choose a weight W1 here and I put this to 0, or I use 0 here and put this to W1, doesn't matter. The L2 norm of this weight and this weight is exactly the same. L1 norm, right? So both solutions are equally valid. So there's an ambiguity in L1 norm. It can eliminate either of the two or neither of them at all. It can also be W1 by 2 and W1 by 2 for both of them. The L1 norm will remain the same. Okay. So what L2 norm does, L2 norm keeps, it doesn't have this ambiguity. It tries to keep both correlated variables either in or out. What that means is, let's say if they were perfectly correlated, then This one has L2 norm of W1. This one has L2 norm of W2. But if I have W1 by 2 and W1 by 2 for both X1 and X2, then the L2 norm is much less, right? It's W1 by 2 whole square plus W1 by 2 whole square whole under root, right? So which is W1 by 2. It's not W1 anymore, right? So your L2 norm becomes smaller. So it will try to, and it will try to make both of them equal, both of the weights for X1 and X2 to be equal. So what happens if I have two penalties, one for L1 and one for L2? Then what will happen is that correlated variables, so let's say assume that this green variable and the blue variable were correlated, they will shrink together and they will be either eliminated together or they will be not eliminated together. So look at these. There are pairs of variables that travel together in the dotted lines, which is for L1 and L2, both penalties together. Yes, Kasina?
Sir, so previously when we saw about correlation, when we took the correlation matrix,
Yeah.
weren't we interested if two variables were highly correlated?
Yeah.
We used to take one of them, right? But
Yeah.
so both of them are getting eliminated. If I'm
Right.
not, then isn't that a disadvantage?
So here what we are saying is that we don't want to make that decision beforehand. We don't want to do that correlation analysis. We want to keep them as groups without having to worry about how collinearity adversely affects the model. Okay, so here it will not adversely affect, it will actually just keep them together. So they are either in the model together or they are not in the model together. Okay. So what elastic net is basically, because it's a combination of L1 and L2 penalty and there is a weight associated. So let's say lambda for L1, but then also beta for L2. There will be two different weights. So look at this contour for L1 loss, right? Which you are familiar with. Look at this contour for L2 loss. A linear combination of these two would be somewhat rounded, but it will have a sharp corner here. This sharp corner is important for variable elimination. And this rounding is important for keeping two correlated variables together. Now, this same effect you cannot get with putting LP as something between 1 and 2, because if you take L L 1.4 norm, you will get similar shape, but you will not get the sharp corner. You will get a rounding effect here. So you will not eliminate variables. That sharp corner is necessary to eliminate variables so that the contours of MSC or the contours of cross entropy graze that corner. Okay, so elastic net basically does that grouping effect and it will also eliminate variables. Okay, so here you can use a regularization for feature selection automatically as well as regularization. Any questions? So lambda is the regularization coefficient. Yes, that's correct. What is lambda? Okay. So let's move to the next one, which is now we are going to talk about. So before this, we were looking at the dependent variable y and comparing every variable xi to the dependent variable y. Now we are going to talk about on the right. Let's say x-axis is feature x1 and y-axis is feature x2. Okay, so it's x1 and x2, and each dot is a data that is scattered along these lines. So what you can see that even though the variance of x1 and variance of x2 are normalized and they are roughly the same, you can see that there is a direction which is the combination. This vector is a combination of x1 and x2, a particular combination of x1 and x2, in which the variance is more. And orthogonal to that, there's another direction which is another combination of an x1 and x2 direction where the variance is smaller. Now in 10 dimensions, there could be such ordering of 10 different directions, which are all orthogonal to each other. The first direction has the highest variance, second direction has the second highest variance, and the 10th direction has the least variance. Okay. So in 3 dimensions, you will have an ellipsoid. So think of it as a discus, like from the discus throw, but the disc itself is also not round. It is also egg shaped, and the thickness is also not uniform. The thickness is also elongated elliptical shape. Okay. So in 3 dimensions, you could have something like uh, I don't know how to draw in 3 dimensions. I will try. Okay, so let's say you have this, but then in the third dimension, it is like this, like small like that. Okay. So this is your first principal direction. This is your second principal direction. And then the thickness would be your third principal direction. So the point of this is that, let's say you have a bunch of points, right? And there is a principal direction along which they are uh, uh, they are dispersed more, and in the orthogonal direction they are less dispersed. So if I take the projection of all these points onto the main direction, so the error in reconstruction of these points would be only this much, the difference from the main principal direction line. Okay. So the errors here are much less. So I can use their projection. What is projection? This is a point, this is the principal direction, this is the projection. So my new point, the approximate point for this point is this point, and this point is only this much far apart from that point because I chose the main principal direction. Okay. So the question is, how do I find these principal directions so that I don't need to worry about some of the orthogonal directions in which the variance is less? Okay. So the way to do that is to take the d dimensional. Now I'm using capital D because I'll use small d later. Start with the d dimensional data, x1 to x capital D. Compute a covariance matrix. Okay, so first you assume that your data is centered and it is zero mean and unit variance in every direction. So now you compute the covariance matrix sigma, right? So this is x transpose x. Okay, and you computing it using x transpose x, and of course divide by n and so forth. Now what you do is you do something called eigen decomposition. Basically you express this sigma. So this sigma is, what is the dimension of this sigma? It is capital D times capital D, right? It has capital D columns and capital D rows. What is the ijth entry of this sigma matrix? The ijth entry is the correlation of xi variable and xj variable, xi feature and xj feature. Okay. So you decompose this matrix. Basically you express this as a product of three different matrices: u, lambda, and u transpose. So what are these u, lambda, and u transpose? These are such that your u matrix is again a d by d matrix, where each column is a unit vector. What is unit vector? Unit vector means it only points to some direction. Its magnitude is always one. Okay. So the columns of u are uh, principal components, principal directions, eigenvectors. Okay. So let me go back here. So let's say you have sigma. Okay. Sigma belongs to set of real d cross d. So it's a d by d matrix. Okay. Now you have expressed this as a u matrix. Okay. And then a lambda matrix times a u transpose matrix. Okay. So what are the columns of u? One column of u is a unit vector. That means if you take the L2 norm of the column, it will be 1. Every column is unit vector. And this unit vector is pointing in some direction. Okay. The second unit vector is pointing in some other direction, and all these directions are orthogonal to each other. That means if you take the dot product of one unit vector with another unit vector, it will be 0. If you take its dot product with itself, it will be 1. So basically it has found a way to rotate the axis into the direction of principal components. And this lambda matrix is such that it is a diagonal matrix. Only the diagonal entries are non-zero. Other non-diagonal entries are all zero. And the diagonal entries are in a covariance matrix will all be non-negative. Okay, they cannot be negative. Okay, so that is your lambda matrix. So it is usually you express lambda as in a order of decreasing eigenvalues. So the top left will be the largest lambda value, then the 2 2 position will be the next largest, 3 3 position will be the next largest, and so forth. So what you can have done with this decomposition is that you have found out all the directions in which the data is spread out, starting with the direction in which it is the most spread out, and then the next orthogonal direction in which it is the next most spread out, and then the third direction in which it is the most spread out, and so forth. So you choose a subset of these d directions. So let's say small d, which is less than d. How do you choose that? So let's say it was in 10-dimensional space. You choose the first three, or you choose those three which represent the 90% of the variance or 95% of the variance. Okay, how do you get that? You basically look at the sum of the eigenvalues, lambda 1 to lambda 10. If lambda 1, lambda 2, lambda 3 gives you 90% of all the sum from lambda 1 to lambda 10, that means those three are enough to represent 90% of the variance or the energy of the data. Okay, so now you can reduce the dimension. You can express these 10-dimensional points into using just 3 dimensions. So you have not eliminated any of the original 10 dimensions, but you have rotated your axis and you have found that there are only 3 directions that are important, and you will use those directions. So your models will have to take only the 3 new directions and not the all 10 directions. Is that clear? Any questions? Yes, Abhinandan?
So again, here I have a confusion. Like,
Hmm.
let's say in a lambda matrix where
Yeah.
we have like a d diagonal
Yes.
every from higher to lower. The
Yes.
first one, let's say for the feature one, that is the
Yes.
maximum, the correlation or the maximum important, maximum measure of
Right.
selecting that features.
Right.
Now, when you told that if you have to select a k feature that has a higher measures, like let's select first k and you take it and you will get some add it the value of
Right.
all, and uh, can it be possible like, okay, remove the first one, remove the d1, d1 represent the first diagonal element of that matrix, and the
Yeah.
next d2 d3 d4, the sum is higher than d1. So rather selecting d1, I can select the two that has a better measure, something like that.
Yeah, but then you have 2 variables, right?
Yes.
You So if you had just selected d1 and d2, you would have higher energy,
Okay.
higher variance, and you would still have only 2 variables. So there is no point in not
Okay.
using the first
Yeah,
one,
I got it, got it, sir. Okay.
right? So let me, for the rest of the class, let me show this again. So let's say you have data points that are spread along the 45 degree, right? It need not be 45 degree, but 45 degree is easy for me to represent. Let's say it is along the 45-degree line, right? So let's say your data is such that it is mostly spread along this axis, okay, but it's little bit spread along 90-degree difference from this, right? So what is your first principal component? It is in this direction, unit vector. The second principal component is in this direction, right? So your U matrix, what will that be? What is this direction? This direction is -1/√2, okay, and +1/√2, right? 1/√2. And what is this direction? This is 1/√2 and 1/√2. Okay, so they are unit norm, and if you take their dot product, if you take the dot product of this and this, it will be 0. Okay, so this is your U matrix. So this direction, this is your major direction, in color red. So this is your major direction, and the major direction is your first principal component. principal component. Okay, the first eigenvector. Okay, then you have the lambda matrix. In the lambda, you will have lambda 1 here and lambda 2 here. What is lambda 1? Lambda 1 is the spread in this direction. Okay, and this lambda 2, so lambda 1 will be greater than lambda 2 because lambda 2 is in the spread in this direction. Okay, so this variance is lambda 2, this variance which is larger is lambda 1. Okay, and then you have u transpose. Okay, so this is u, this is lambda, this is u transpose. Is that clear? So your sigma will be represented like this.
So
So what I can now do is I can express every point by not using the second direction at all. I can get rid of this. I can multiply every x, right? So I can take x transpose this one, u1, right? This u1, just this, and that is my feature. So if x had how many components? Two components, x1 and x2. If I take x transpose u1, I'll get only one component, which is the dot product of x with just the first vector. Okay, so I've eliminated, I have reduced the dimension from 2 to 1. That is basically as good as saying that I will set this lambda to be 0, lambda 2 to be 0. Any questions? Let's look at the chat. Can you explain PCA from the start? Yes. Yash, what's your question?
Sir, could you once more tell about the SVD theorem that you just said?
Yeah. So basically, what we are saying is that this sigma matrix that you have, by definition, it is going to be positive semi-definite, right? Because it is positive semi-definite, you can do an SVD where you can singular value decomposition or eigen decomposition, where you can express this as a product of three matrices, U, lambda, and U transpose, where U is orthonormal. Orthonormal means each column is unit norm. It's not right, and then each column, its product with another, its dot product with another column is going to be 0. They are going to be orthogonal directions. They're going to be at 90 degrees to each other in the capital D dimensional space. And then lambda is going to be a diagonal matrix, and each diagonal element will tell you for the corresponding direction encoded in the columns of U, what is the spread of data along that direction, what is the variance of the data along that direction.
Yeah,
Okay, so
Professor, I think the decomposition statement written is a bit, because it's U lambda V transpose. I think V
I'm sorry.
transpose.
Yeah. So actual singular value decomposition has V transpose, but in eigen decomposition, it actually is same as
Oh, okay,
it's
okay.
the same.
Okay. Thank you.
So it's a special case of SVD.
Yes, thank you, Professor.
Okay. Korang?
Sorry.
Okay. All right. So basically what you are saying is that I will keep only the directions which are the projections. Okay. Uh, so what is a projection? Projection is basically, let's go back to that slide. So let's say if I had x1, if I had 10 dimensional space, right? So if I had x1, x2, all the way up to x10, right? And this is my vector x. Okay, and I take only the first two components. Okay, u1 and u2, which is u11 all the way up to u10 okay, and u21. Let me erase this. Eraser. Okay. So I had u11 and all the way up to u10 and then u21 all the way up to u sorry, yeah, u12 u12 all the way up to u10. Okay, if I take this times this, and then this times this, I will get two numbers. I'll get two new numbers, phi1 and phi2. Okay. So from 10 numbers, I have reduced to two numbers. So now my classifiers have to use only two numbers. These are the projections of the original data onto only two directions, and I am not using the rest of the eight directions. Okay. But that doesn't mean I have eliminated any of the original axis. I have just reprojected them onto two dimensions. Okay. So that is a unsupervised way, because here I didn't think about what is the class, what is the regression label, and so forth. Okay. So this basically covers how to reduce dimensions, how to select features, how to select subsets. Now let's look at some popular features. Okay. So let's look at features for images, audio, and text. And a lot of these are before deep learning. These features were all inspired by, they came from domain knowledge. You understood something about images, so you could decide, okay, let me extract this from the images, or let me extract this from audio, let me extract this from the text. So we'll study that. Uh, Although a lot of it has become redundant since deep learning came, but it's still good to know that domain knowledge is important to extract some features. So let's start with images. Okay, so here are some examples. This is not comprehensive. It's only a set of examples of features that you can get from an image. So what is an image? Image is your W cross H two-dimensional array, right? So your image, sorry. So what your I'm sorry, this I need to get used to this. So what your image is, it is basically, let's say, W cross H two-dimensional array, but that's a lot of numbers, right? So let's say your W is 640 and your height is 480. I don't want to deal with so many numbers and call each of the pixel as a single feature. W times H is a lot of features. I want to extract only 10 features or 100 features. So what I want to do is I want to summarize this into a set of D features. So what do I do? So I extract some features. One example is that I take all the pixels and let's say if it is black and white, it is a grayscale. I compute a histogram of grayscale intensities from 0 to 255. Okay, so this is my histogram. Now it has 255 different features. I can reduce it further by saying that I will use only some statistics of this histogram, such as mean, median, mode, skew, kurtosis. Okay, so now I have these 5 features. If my image is a color image, then instead of a grayscale histogram, I will use a color histogram. So what is a color histogram? You have red, green, and blue. So you have a cube of pixels. So 255 times 255 times 255, that's a lot of different bins. But let's say I can reduce it. I will just use the green and the blue pixels, or I will use something like that, right? So, and then, or I will just, I will quantize certain regions of the color space, RGB space, and I will use only those quantized bins. So that is one way. Then you can extract features based on shapes, something called hue movements. Just look it up. What hue movements does is basically, if you have a shape, an image like this, like what is A, and you rotate it and resize it into image B, then the hue movements don't change. The hue movements only change when the shape changes to C. So let's say you want to detect cars, and the car can be big or small, the car can be slightly rotated and so forth. Then hue movements will tell you, will be a good match to match different shapes. Then there is something that encodes texture. This is called gray level co-occurrence matrix, GLCM. And how texture is encoded is, you think about fine, let's say, stripes on the butterfly, or a zebra or something. Then how do you encode that there is a lot of white and black pixels that occur next to each other? Okay, that's what you want to encode. So if you look at the image closely, these are your gray levels. Okay, this is a gray level, this is a lighter gray level, this is white, this is dark, this is medium, and so forth. Now let's say we convert this into numbers from 0 to 255 or 0 to or 1 to 1 2 3, three different levels. So you have the numbers will look like this, the pictorial will look like this. Okay, so this is 1 because this is very dark, 2 is medium, 3 is very bright. So now you count the number of times 1 and 2 appear together. So now here these are not positions, but these are different gray levels, 1 2 3, and let's say up to 255 or 256. And this is reference value and the neighbor value. Okay, so the reference picture and the neighbor picture. So when 1 and 2 appear together, basically we count it as for this 1th row and the 2th column, we will call it as, we will count these 1 2 and 3, and we will put the number 3. So now you get a, if you have L different levels of gray level, you will get an L by L matrix, which becomes your Haralick texture features. Okay, so this comes from your gray level co-occurrence matrix, and then you can summarize it even further and get some more features out of some reduced set of features out of it. And if you want to extract different orientations of lines, so if you have an urban scene versus landscape scene, in urban scenes you will see a lot of buildings, so you'll see a lot of vertical edges, whereas in rustic scenes you will see the horizon, so you will see a lot of horizontal edges. You will filter the image with some convolutional features. Simple ones are these Har features. So you basically find out, you put this small filter on top of the image and you slide it, and you look at the response, and then you can summarize it. So these are your Har features. So without going into detail, because that goes into image processing, I would encourage you to look at some of these features. This is how some of these features were extracted earlier. Okay. Now we put features and then features of features and then the classifier all in a single row and treat them and train them using gradient descent, and that is called a deep neural network. Similarly, in audio, the most popular feature that is used is this MFCC, mel frequency substral coefficients. What that is basically, it is based on the knowledge of how sound waves are, that they are arranged in log of frequency, like the structure of the, so if you are playing piano, you know that one C note and the next C note, there is a log relationship in their frequencies, right? So it's like twice that of the previous octave and so forth. So for speech processing, a lot of that is used. The way it is used is, let's say you take the speech signal and you take its different frames. So that means you take, let's say, only 100 millisecond at a time or 1 second at a time, and you will analyze that. So that's a frame, the window, the window that you will analyze. And you will do some pre-emphasis, means you will suppress the high frequency and low frequency, because you don't think that contains your speech signal. And then you will compute the Fourier transform, and then you will basically summarize the Fourier transform in different frequency bands, which are arranged in a log scale. And there are these summarizations are actually based on overlapping bands, and the overlapping is in some triangular fashion. So it's based on uh, people who had studied audio signals very deeply. Then you take the log of that, because loudness decibels is in log scales, and based on that you get the MFCC coefficients, and you use those in your classifier. So these MFCC coefficients become your x1, x2, x3, etc. Similarly, in text, there are special features. One is called a bag of words. So what that means is, let's say you have a text. India posted a score of this in the allotted overs in the third deciding test, etc. So you see that in this text, there's a lot of things that you don't want to encode, which is numbers, for example, or words like in, the, because these are like very commonly occurring words. The informative words are India, Virat, Kohli, uh, Classy, Adil, Rashid, David, Willie, etc. Right? So these are informative words. So you want to form a vocabulary of all the informative words. These are the not so common words, right? So let's say your goal is to classify whether a paragraph is a positive sentiment or a negative sentiment, or whether it pertains to India's victory or India's loss or draw, right? So you want to classify automatically each text paragraph into that. So you would actually take all these informative words and form a giant vocabulary. So let's say 10,000 informative words, all possible words. And then you fill them with counts of how many times that word appears in this particular paragraph that you are trying to classify. And you can normalize those counts, and basically that becomes your bag of words model. That means the order of the words doesn't matter, only their counts matter. So that's a bag. It's the order inside the bag doesn't matter. Okay. If you're not satisfied with a single word, you want to look at the order of the words, then you look at, let's say, 2 words at a time, 2 neighboring words at a time, and it becomes a bigram, 2 gram, 3 gram, etc. So these are features for text. More sophisticated features than just a bag of words is something called term frequency, inverse document frequency, TF-IDF. So what that means is that you not only look at how frequent is a word in a particular document, okay, how frequent is a word, but you also look at the inverse document frequency, as in that how much is the word frequent in all the paragraphs versus how much is the word frequent in this particular paragraph. You look at the difference between the two. So if a word is very frequent in lots of paragraphs, then it's an unimportant word. If a word is less frequent in all the paragraphs and yet you see it here, then it is must be informative for this paragraph, right? So that is the whole intuition behind it. So term frequency is nothing but frequency of that term, okay, divided by frequency of all the terms in all the documents. Okay, and then inverse document frequency is that for this particular document, okay, what is sorry, so term frequency is in this particular document. D is a document, and inverse document frequency is that what is the frequency of this word in all the documents, D, in the entire corpus where each document belongs to the D. So here document means, let's say for example, the paragraph. So here you would take the inverse of all the document frequency. So if the term appears too many times in all the documents, then you will get a smaller value of that, and then it will de-emphasize the term frequency. Okay. If it is a rare word, then it will emphasize the term frequency more. Okay. So now you do this for all the words that you have in the vocabulary, and then you have a feature. So you have a 10,000 dimensional feature if your vocabulary size is 10,000. Okay. And then all these 10,000 features are not important. So you will do feature selection, you would do variable elimination, or you would do uh, elastic net or L1 penalty based feature elimination. Okay. That's it from the lecture. Any questions? Yes, Ashish.
Sir, in the case of um, what I was asking, I asked a question in the chat. Can you look up that question? I also
Yeah,
forgot. I think the other person can take up the question. I can just ask it after the other person.
where is your question? I don't see it. I have Divya's question which says, please explain PCA again. Oh, Ashish. So it means,
I'll recall
so
and I'll ask
similar
it
features
after.
will have
Yeah.
similar coefficients. Similar features
Oh,
will have,
yes.
yeah. So similar features will have similar coefficients for elastic net, not for lasso.
Okay, so
For
for
lasso, it is
for
not
example, in the case of ElasticNet, if you want to see like how collinear or like in general how similar features are, whether they'll be zero at the same time or rather they'll have the same value which is non-zero. So we are just concerned about the similar values, right?
Right.
Yeah, correct. Thank you, sir.
Then Aryan has a question: how is L1 error computed in text? So I don't know about L1 error, but L1 norm of the of the weights would be, so let's say you have 10,000 different words in your vocabulary, so you will have 10,000 different weights, right, for a linear regression or logistic regression model. So you can just add up the absolute value of all the weights. That is the L1 now. Okay. Priyam?
Yeah, so initially, when you were teaching the heat map, you said if there are two features which are highly correlated, do you always discard one, or there are some exceptions?
Depends, right? If you're using elastic net, then you don't need to discard.
Okay.
If you're using any other method, then it is better to discard.
Okay, thank you.
Gorang?
KL filter and what will it do?
Can you repeat? Your voice was very cut off, very broken.
In the audio signal, audio case, filter band.
It's still not very clear, but I think you're asking about the audio, right? So basically you will get different. I'm sorry?
Filter bank. I'm typing. Okay.
Yeah, the filter bank, right? So each filter in the filter bank will give you one coefficient, one variable. And that one variable will be for one small portion of the speech. You will, because you are doing windowing, so you will also shift it along the time direction. So you will get something called a spectrogram. So you will get different frequencies. So basically, let me go back here. Let me see where I have space here. So what you will have is that you will have a feature which will look like an image. You will have different time bins here, and you will have log frequency bins here. Okay. So each of those filter bank will give you for one time, it will give you for one frequency band, it will give you some response. So for each time, each window, you will get responses in one column. And then for different windows, you will get different columns. And so let's say if you have 150 windows and you have 10 bands, you'll get 1500 features. Okay. So that is your feature for your 150 windows of a speech signal. Yeah, time frequency analysis. Does that answer your question, Goram?
Yeah, that was the query. And another thing about that shape information and the like orientation information, can we use Sobel filter and all those things? Sobel.
Yes. So Sobel filter will give you edge response, but then again, it will give you one edge response for every pixel location. So it is still quite high. So you might want to then summarize it using some other statistics.
Okay, like line detection and then equation of that line.
Yeah, something along those lines you can do. Or the percent of pixels that have high line response, something along those lines. You'll have to summarize it.
Okay.
Yeah. So there's a question from YouTube, which is difference between multi-collinearity and correlation. So they are basically interchangeably used. Correlation is between two pairs of variables. Multi-collinearity means that you can have multiple variables that are correlated. So, but they are interchangeably used in informal talk. Any other questions? Subhakar, are you here? Hello, Sudhakar? Anything to cover from your side? No, I guess that this is it. We'll be releasing the assignment soon. And the assignment, I believe, is going to be about classifying audio signals into different classes, like bark of a dog, crying of a child, and so forth. Okay, so you will be using a toolbox to extract features, and then you will be doing feature elimination, feature selection, elimination, and then training a classifier.
Sir, regarding the audio processing,
Yes.
I tried to install audio py. It's somehow not working. And when I checked through the GitHub repository, many people are having the same problem. It's not being resolved actually.
Okay.
most of the.
We'll find you some other way to extract audio features.
Yeah, thank you, sir.
Okay. All right. Sounds good. So looks like there are no other questions then. Hrithik?
So MATLAB has a feature of audio processing, I think.
Yeah, MATLAB does have it, but we are trying to keep everything in Python. So I'll find a good Python library.
Okay, cool.
All right. Okay. All right. So take care, everyone. Okay. I hope you enjoyed the lecture. Thanks.